Okay, so let's do an example on natural convection. So let's say we have a flat plate. Let's take a simple flat plate, and its surface, the upper surface of the flat plate is at a temperature of 400 Kelvin, and this air surrounding it is at 300 Kelvin. And uh, note that the air is stagnant, so it's not moving. So U infinity is 0 meters per second. And let's assume that the plate is 2 meters long, and it runs infinitely into the page. So in this scenario, it's obvious that we will have heat transfer due to natural convection because there isn't any movement of air. There isn't any air being forced to flow over this plate, so we'll have natural convection, and we need to find our Q double prime, that's the heat flux. So we don't know what are values for thermal conductivity or heat transfer coefficients are. The only thing we know is the dimension of the plate and the surface and the surrounding temperature. So like the procedure that we follow in forced convection, we'll follow the same procedure here as well. The first thing we'll do is we'll find the film temperature so that we can find out what the properties are at that value. So in this scenario, our film temperature will be Ts plus T infinity by 2. So it will be T 350 Kelvin. And we'll look up the properties of viscosity, thermal conductivity, and other properties at 350 Kelvin in table 8.4. So I've already looked these properties up. So these for your viscosity will be 20.92 into 10 to the power minus 6. And I've mentioned it. I've mentioned how to look these properties in the solved example done on external free force convection. So if you don't know how to look up these properties, please go to that video. Our thermal diffusivity is 29.9 into 10 to the power minus 6 meters square per second, and our Prandtl number is 0.7, and the thermal conductivity of air is 30 into 10 to the power minus 3 watt per meter Kelvin. So if you see that Greshoff's number and Rayleigh number play an important role in a natural or free convection, and the only thing that we don't know in the formula of the Grashof number is the beta, that's the thermal expansion coefficient, and we can calculate or we can estimate the uh, thermal expansion coefficient by using the film temperature. So our thermal expansion coefficient will be 1 divided by the film temperature, so it will be 1 divided by 350 Kelvin. And please note that the temperature while finding beta must be in Kelvin. It has to be the absolute temperature. So now our next step is to characterize the type of flow. So now because our U infinity is 0, and the formula for Reynolds number has U infinity L by mu, because this is 0, we can't say anything about the Reynolds number, but we still have a flow being created due to natural convection, and that flow and we need to characterize what is the nature of that flow. So we'll do that using the Rayleigh number, and the definition of Rayleigh number is that it's the product of Grashoff's and Prandtl's number, and the only difference between the formula for uh, Grashof number and Prandtl number is that the denominator is different. So you'll have a mu times alpha here, whereas for Grashof's number you have a mu square. And on substituting these values, we get the Rayleigh number as 3.6 into 10 to the power 9. And for natural convection, if the Rayleigh number for an external flow is greater than 10 to the power 9, that means that the flow is turbulent. So in our case, our Rayleigh number is greater than this threshold value, so we will have a turbulent flow. So for our next step would be, for this particular scenario, looking up for a correlation for Nusselt number. So uh, before we jump into the correlation of a result number, we must look at different scenarios that you can have when you have a flat plate. So there are four scenarios you can have. One is that if your top surface is hot and your surrounding is colder, your top surface is cold and your surrounding is hot, so you will have heat being transferred from the surrounding to the plate, and in that scenario you will have currents that will be flowing towards the plate, and your flow will look something like shown in figure A. Now the second scenario is that your bottom surface may be hot and the surrounding may be cold. So in that case, you will have heat being transferred from the bottom surface of the plate to the surrounding. And in that case, your currents will look something like this. The next scenario is when you have when your top surface is hot and your surrounding surface is cold. So this is the scenario that we have right now. Our top surface is hotter than the surrounding, and that's how the currents will look like. And the last scenario is if your bottom surface is hotter than the surrounding. And if you realize something that um, figure A and D are mirror images about the plate axis, and figure B and C are mirror images about the plate axis. So that means that the correlation in these cases will almost be similar, like correlation for A and B and correlation for B and C. So in your text, equations 9.3, 9.31, and 9.32 give us the correlations for Nusselt number for these different scenarios. So for our scenario, we have the upper surface of a hot plate given. So we have our upper surface is hot, and you see that these correlations will also be true if the lower surface is cold. So that means it will be similar to scenario bottom surface B. Okay, so we've seen that our Rayleigh number is 3.6 into 10 to the power 9. So we use equation 9.31 for our hot plate. So you need to be careful when you read the labels or the titles of these equations and the conditions. So we cannot use equation 9.3 because our Rayleigh number does not fall in this range. Our Rayleigh number is 3.6 into 10 to the power 9. So we use equation 9.31, and it's true for all Prandtl number. So we need not worry about that. So to find H, our relation for H is Nusselt number times K by L. We have already found out K and we know what L is, and our Nusselt number will be 0.15 into Rayleigh number to the power 1 by 3, which gives us the value of 494.6. So on substituting this value in this equation right here, we get H as 7.4 watt per meter square Kelvin, and using Newton's law of cooling, we can simply find out Q double prime as H times the temperature difference, which will give us 740 watt per meter square. So the important thing to note here was the additional thing to note here was you need to also identify what surface of the plate is hot or cold with respect to your surrounding.